All right, so we're going to work on chemical reaction types. We're going to go in a little bit more detail than what you needed for the assessments on the course. So just make sure you're hearing all the little tidbits as we get through. So chemical reactions, reactants on the left, products on the right. And what happens? We have a chemical change, so new substances are formed in the products. Sometimes you can tell that by the facts. It fizzes, there's a smell change, a color change, a temperature change. We'll talk a little bit more about that as well. And it creates a new substance. We're regrouping the atoms, but we still have conservation of mass. So if you have 10 carbons on the left, you still have to have 10 on the right. They just can be arranged differently. And your properties of the products will be different than the properties that those reactants have. Why? Because they're new substances. Hey, here's your basic types of reaction here. The ones that you may not have seen so much yet is down here. This is still a double replacement reaction. It's still cation swap. It's still two couples, but it is classified one level higher as a neutralization or an acid-base reaction. Okay, and that means there's one acid and one base on the reactant side, and they form into a salt and a water. A salt doesn't have to be sodium chloride. It can be any ionic. So it's really an ionic and a water. Okay, but these are just a special type of double replacement. So sometimes they want you to go into a little bit more detail when you're identifying things. Right, we see the state symbols there. That should make sense. Aqueous, remember, that's when it's dissolved in water, so it's a solution. Some things to remember: acids are always aqueous, so they are always in solution, so they always have that AQ. If you have a solid on the right side, its other name is a precipitate. It rained down at the end of the reaction and formed a solid in the bottom. All right, copper 1 sulfate reacts with magnesium chloride. What type of reaction and what are the products? Same as always, you can pause the video and then try it on your own. You may want to go as far as balancing the whole thing because that gives you practice. I'm not balancing anything today. So when you see things at the end, they are not balanced, so they are not in proper grammar. Yeah. So we have copper 1 sulfate, copper with a charge of +1, sulfate with a charge of -2. Polys get parentheses and we crisscross. Copper sulfate. Okay, I do not have to show those parentheses for this guy because it's with a 1, and that's how I'm able to take that off. And we don't show the signs in our chemical reaction. So copper 1 sulfate is reacting. That means these guys are reactants. They're going to be on the left side with magnesium chloride. Magnesium, 2+ charge, he's in group 2. Chlorine, 1- charge because it's a halogen in group 17. MgCl2. So these are our reactants. What type of reaction? So now we go through, we have two couples. What's a couple? 2 or more elements. Okay, both sides have 2 or more elements. So these are both couples. So we have 2 couples, double replacement. Okay, so they're going to swap their cations, or you can use it as the FOIL method, inside and outside. So outside would have copper going with chlorine, copper 1. So keep the charge that was on there from the beginning. It's a transition metal. It charges change, but if they don't tell you, you keep the same one. And chlorine. Okay, so this guy is a basic. It just goes right together. And magnesium is going to be with sulfate. Magnesium, 2+, sulfate, 2-. And again, those guys are already equal and opposite, so you can just smush them together. And those would be our products. What are the names of the proper products? Copper 1 chloride. Remember, "ide" on the end to let you know that it is a compound. Magnesium sulfate. This one has an 8 on the end to remind you that there's oxygen because you used a polyatomic ion. Okay, what type of reaction and the products? We got everything answered there. We can move on. Fluoride gas or fluorine gas, either way, reacts with magnesium chloride. What type of reaction? What are the products? Fluoride gas, F2. Brinkelhoff, okay, with magnesium chloride, MgCl2. What type of reaction and what are the products? Okay, so just looking at the left side, you could say, well, it could be a synthesis or it could be a single replacement. What is it more often than not? We're going to go with a single replacement. Okay? So it'd be odd that you just stuffed in more fluorines with the chlorines. Okay? Fluorine is a halogen. He's a negative. Chlorine's also a halogen, but he wouldn't have to be a halogen. What are you just looking for? That they're both negatives. They are both anions. So the anion is going to kick out the anion from the couple. It's going to be a bully. So fluorine's going to kick out chlorine. Chlorine's now going to be by himself. Chlorine's also a Brinkelhoff. So it's Cl2, and then magnesium is going to be with fluorine. And when we check the crisscross, it has the same crisscross only because chlorine and fluorine are halogens, so they have the same charge. Okay, otherwise you do want to make sure you're re-crisscrossing. Okay, and now we have our products, chlorine gas and magnesium fluoride. All right, I did not have to use a Roman numeral here with the magnesium because his charge is always 2+ because he's in group 2. He's not a transition metal. Only transition metals need Roman numerals in your name. Okay, so let's make sure we got everything. Halogens. How did I know he was a halogen? I didn't write down the whole list of halogens here, so let me do that quick. Bromine, iodine, nitrogen, fluorine, hydrogen, oxygen, fluorine. The Brinkelhoffs always, when they are alone, unless they're in solution, are going to have their twin with them. That's how I knew fluoride gas and chlorine gas were going to have their 2s there. Okay. Now, since it's a single replacement for year 1, you do want to know if that guy is going to react or not. And the way we know is halogens. If it's a stronger halogen, more electronegative, then it is going to be more reactive. So it is strong enough to kick out somebody. Fluorine has the highest electronegativity, so I don't even have to look at the chart. He has an electronegativity of 4. You can think of him as fluorine to help you remember. But he is the most electronegative element out of all of them, not just the halogens. So he is going to be strong enough to kick out fluorine. So that reaction does occur. All right, C3H8 reacts with oxygen gas, Brinkelhoff, there's 2 of them. What is the type of reaction? Okay. C3H8 and O2 is going to fit a standard format. While it looks like it could be single replacement or combustion, you always go with the one that is the most specific. It is definitely a hydrocarbon there in the front, okay, because we have 3 for our X's, 8 for our Y's, and 0 for our oxygens, which is a typical hydrocarbon, would just be those C3H8 plus oxygen gas, and that always yields water and carbon dioxide. Hydrocarbon combustion products are always water and carbon dioxide. So I don't have to do any fancy crisscrossing or foiling or anything like that. Now, sometimes it's going to show up like this, and it's going to put an energy on a specific side. This one has the energy on the product side, which means it was released in the reaction because we released it and then we could collect it because it's a product. It's separate now from the hydrogen and the carbon dioxide. It released, it exited, it is exothermic. Okay? If you see an energy or a heat or anything like that that can produce energy, if you see it on the reactant side, it would be endothermic. Okay, now this does not change how my formula looks. So some people get confused with synthesis and decomp reactions. If you see energy there, that does not count as a chemical product. So that does not mess up your cheat codes of a synthesis has 1 product and a decomp has 1 reactant. So it can be 1 reactant plus energy. It It can be one product plus energy or not, but it is still classified that same way. Decomposition of water. What are the products and state symbols? Decomposition of water. Decomposition, we already know the type of reaction, but the clue is, what is decomposition? Breaks down into simpler substances, starts with one reactant. So our one reactant here would be our water. And this is a binary decomp. There's two elements, so it's binary. So it's just going to split into hydrogen and oxygen. Hydrogen gas and oxygen gas, which are Brinkle hops. So make sure you have those little twos there to help you out. Okay, so those are our products. What are our state symbols? So water, you typically, unless they tell you otherwise, you would tell you that they are a liquid. And hydrogen gas and oxygen gas, those guys are light enough diatomic, so that those guys are also gases. When you get further down on the halogens, those guys are not gases anymore. Those guys are too heavy, but everybody else here is a gas when you are doing those state symbols. So now you can even predict state symbols on the product side, even if they don't tell you. All right, type of reaction, state symbols, and predict the products between H2SO4 and sodium hydroxide. Look at that. That is sulfate, and he's crisscrossed with hydrogen. If you see an H plus in front, it's an acid. Okay, which acid? Sulfate becomes sulfuric acid. And this is sodium hydroxide. So right now, I know I have two couples, so it's a double replacement, but I should also notice I have an acid, and if I have an OH in back, I have a base. So this is also going to be an acid-base reaction or a neutralization reaction. So you can go a little bit deeper on that. When we have a neutralization reaction, we're still doing the same thing as a double replacement. Inside and outside. Oh, how do I know which one's inside and outside? Polys get parentheses. There, inside, outside. Okay, when you're putting these together, H plus OH minus becomes two H's and one oxygen. We just have it here in molecular format because that's how we can see it's the acid and base being neutralized. And that's why acids are always aqueous. They need that water to propagate. And it's a way to help us remember that even if it's a really strong acid, it's still going to have some base particles. And even if it's a really strong base, it's still going to have some acid particles because they are in water when they got neutralized. Neutralization reaction always gives you a water and a salt. In this case, our salt is sodium sulfate. So type of reaction, double replacement, but specifically acid, base, or neutralization. State symbols predict the products. Okay, so the only thing we have left to do is predict the products. So I'm going to clear off everything else. Acids are always aqueous. They're always in solution. Sodium hydroxide is not always in solution. It's a base, but I go back up here, pellets. Pellets are solids. So we're going to mix the aqueous solution of sulfuric acid with the pellets of sodium hydroxide. We're going to get water. Water is not aqueous. Water is a pure substance, so it gets an L for a liquid. And then sodium sulfate. How can I predict what that product is? Is it going to be a precipitate that rains down as a solid, or is it going to stay in a solution in the water that's left over right there? So even though this is an acid-base reaction, definitely not something you want to drink. Just because something's neutralized doesn't mean it's safe. And what's the chances that we actually neutralize the acid and base perfectly at 100%? So a neutralization action is balancing the acid and base, but don't expect it to be perfect. So let's head back to that solubility there of sodium sulfate. Okay, so ionics are typically soluble in water, like dissolves like, but that is just an overall general rule. It's really not specific. If you remember those graphs, it really depended a lot on temperature if it was able to be dissolved. So you really want to check with a solubility graph like we did, or you could be shown a solubility chart to help you out. So here's an example of a solubility chart, and you just look and see, are they on the left or the right? Sulfates are on the left, so they are soluble. Soluble means dissolved in water. Insoluble means not dissolvable in water. So these guys are soluble in water. So you would give it be an aqueous because there's water there. Now, if there was no water there, he could just be a solid. We don't know what else is going on. But in this case, we definitely have water there, and he's soluble in water, so he would be aqueous. Okay? If we found something on the right, then it would be a solid. And if it's a solid on the right side, it's called a precipitate. Barium reacts with iron 2 chloride. What type of reaction and what are the products? Barium reacts with, so reacts with is a code for plus. Iron 2 chloride, iron with a 2+ charge, chlorine 1- crisscross, FeCl2. All right. Single element and a couple. Single and a couple is single replacement. Okay. And what? Same kicks out same. So barium is in group 2, so it's a cation, positively charged ion. Okay, and who is it going to kick out? It's going to kick out the positive. Okay, you can only kick out somebody with your same charge. So barium's now going to be with chlorine. And we're going to re-crisscross. And this time again, we're getting lucky on the crisscross. They're the same, which means our balancing is going to be pretty easy, but you still want to do the crisscross to make sure. Okay, so barium is now with the chlorine, and the iron was kicked out and he's by himself. So those are our products: barium chloride and iron. All right. And what a type of reaction and what are the products? We got that there. And does this reaction occur? So in this case, we have to see who's stronger. Earlier, for single replacement, we were dealing with the anions, and we just had to look at the electronegativity of the halogens. To figure out the reactivity or the strength of the cations, you need the table. Okay, and so we find barium up here and we find iron. Barium is higher up, so he's stronger. So this reaction does occur. And that's all for today.